students, in this video we are going to explain about a project titled Helmet Detection using Single Shot Multi-Box Detection and YOLOV3 algorithm. So now coming to the introduction part, the application of helmet detection using SSD and YOLOV3 algorithm has the potential to revolutionize safety practices in various industries, fostering a safer working environment and reducing the likelihood of accidents and injuries. As the technology continues to advance, it holds great promise in not only ensuring the proper use of helmets, but also in extending its capabilities to detect other safety gear and compliance-related aspects, further enhancing overall safety standards. It divides the input image into a grid and predicts bounding boxes and class probabilities for each cell within the grid, allowing for faster and more accurate object detection. So our main objective for this project is that the technology is to improve safety practices in industries like construction, manufacturing and transportation by ensuring that workers and individuals adhere to safety regulations and wear helmets as required. By providing real-time insights to safety supervisors and personnel, the system can mitigate risks and prevent potential accidents and injuries. Additionally, the scalability and adaptability of this approach hold promise for extending its application to detect compliance with other safety gear and protocols, further enhancing workplace safety standards and fostering a safer working environment for all. By combining the strengths of SSD and YOLOV3, the helmet detection system can provide a robust and efficient solution. The deep learning models are trained on annotated datasets, allowing them to learn to recognize helmet-wearing individuals with high accuracy. Now coming to the requirements part, we have two types of requirements, that are hardware requirements and software requirements. In hardware requirement, operating system as Windows is required, processor i5 and above, minimum 4 GB of RAM is required, hard disk 20 GB and above. Coming to the software requirement part, Python IDE, that is 3.7 version is required. Now coming to the methodology part, first generate and load SSMD and YOLO model. To create the single shot multi-box detection, that is SSD and YOLOV3 models, the first step involves generating and training these deep learning models. SSD is an object detection model that efficiently predicts bounding boxes and class probabilities for multiple objects in an image. YOLOV3, on the other hand, is another object detection model that divides the image into a grid and predicts bounding boxes and class probabilities for each cell. Second, upload image. With the SSD and YOLOV3 models ready, the next step is to upload an image into the system. This image can be from a surveillance camera, a drone or any other source where helmet detection is desired. The image serves as the input for both the SSD and YOLOV3 models to detect helmets within it. Third, detect helmet using YOLOV3. Using the uploaded image, the YOLOV3 model processes the image and performs real-time helmet detection. It divides the image into a grid, predicts bounding boxes and class probabilities for each cell, and identifies helmets present in the image. The output includes the coordinate of the detected helmet bounding boxes and their corresponding confidence scores. Fourth, detect helmet using SSD. Similarly, the SSD model processes the uploaded image and performs helmet detection using single-shot multi-box detection. So here we are talking about SSMD. So in this, the model predicts bounding boxes and class probabilities for potential objects, including helmets, in a single pass through the neural network. The SSMD model output also provides the coordinates of the detected helmet bounding boxes and their confidence scores. Fifth, loss comparison graph. During the training phase, both SSD and YOLOV3 models undergo an optimization process to minimize their respective losses. The loss function measures the similarity between the predicted bounding boxes and the ground truth bounding boxes. A loss comparison graph visually represents how the losses of the two models evolve during training, providing insights into their learning progress and potential overfitting and underfitting issues. Sixth, accuracy comparison graph. As the models are trained on annotated datasets, their detection accuracy is evaluated on validation or test datasets. An accuracy comparison graph illustrates the performance of both SSMD and YOLOV3 models in terms of the ability to correct detect helmets and images. So now coming to the execution part. To execute the project, first we need to open the code folder. Here we have a folder named as PyCatch. In this we have a Python file containing the Python script in it. And another folder named as bikes. In this we have some images of bikes. And this folder dataset containing many files in it for testing and training the dataset. And this folder models containing .h5 files which contain the deep learning algorithms information. These .h5 files can be loaded into the project during runtime to utilize the trained model for various tasks such as making predictions on new data or performing specific operations. And this folder YOLOV3 model has some datasets over here also. Helmet detection file and YOLO detection are the two Python files which are containing the Python script in it, and this is the main Python file. And here this is the run.bat file. Instead of executing the program in command line interface, we created Windows bat file to execute the project. Now to run the project, double click on run.bat file to execute the project. Here this is the graphical user interface. With this we are interacting with the program. So now click on generate and load SSMD and YOLO model button to generate and load both models. So here on this screen in text area we can see both models loaded. And now click on upload image button to upload image. So now here I am selecting this image. And now click on open button to load image for getting the output. So here on this screen image loaded, and now click on detect helmet using YOLOV3 button for getting the result. So here on this screen YOLOV3 identify helmet with detection rate as 0.92%. So now closing this image, click on detect helmet using SSMD button to get helmet detection using SSMD. So now here on this image SSMD detected helmet as with 0.89% weight. So now closing with this, click on loss comparison graph button to get loss of both algorithms. Here in this graph, x-axis represents training epochs or iterations and y-axis represents loss values, and we can see both models loss value decreases when epoch or model filtration increases, and the model will be considered best if its loss value decrease in each approach. And from this graph we can see YOLOV3 loss is less compared to SSMD. So now closing this graph, click on accuracy comparison graph button to get the accuracy graph. So here in this graph, blue line for SSMD and orange line for YOLO. So in this graph, YOLO performing better than SSMD in accuracy also, and both algorithms get accuracy more than 90%, but YOLO is better than SSMD. So now closing this graph, coming back to the conclusion part. Ultimately, helmet detection using SSMD and YOLOV3 algorithms serves as a testament to the transformative potential of computer vision in improving safety standards and protecting the well-being of workers and individuals. By embracing such innovative solutions, we can create safer environments, reduce the occurrence of workspace accidents, and strive towards a safer, more secure future for all. The success of this technology not only lies in its ability to detect helmets, but also in its potential for future expansion and include the detection of other safety gear and compliance related aspects. As this technology continues to evolve, it holds great promise for enhancing workplace safety practices across industries, fostering a culture of safety and responsibility.
For updates on latest project videos, please visit True Project's YouTube channel and subscribe.